Hello, students. Are you ready for part 2, where you can learn how to calculate the percentage of your home heating needs that are provided by solar energy? In part 1, we showed how to calculate the net heat loss coefficient. In other words, the BTU losses out of the house per degree day. It includes all the surfaces of the house and the air infiltration. The only thing it doesn't take into account is the south-facing windows, because south-facing windows or greenhouses or trombe walls or water walls all have a net heat gain. Next, we're going to look at what we do with this net heat loss coefficient. So if you go back to your handout on solar savings fraction from week number 5, open it up and scroll down past the net heat loss coefficient, past the NLC, and now you're on number 2 of that handout. It's called the load to collector ratio. It actually has load/collector ratio in writing, and then it says LCR and number 3 solar savings fraction. So take a look. See, load to collector ratio, LCR, and 3 solar savings fraction, SSF. That's what they stand for. Now the load to collector ratio is just what it sounds like. It's the heat load of the house divided by the square foot of the collector area. The heat loss of the house we know because that's the NLC that we just calculated. See right there? Divided by, that's what that slash is, the A sub C, which is the south-facing glass. In this case, 55 square feet. So if you take a calculator and you calculate that out, 9,763 divided by 55 gives you 177.5. Now that number is known as the LCR, the load to collector ratio. What do we do with that? We look it up on the table. So let me scroll down to the table for you, and we'll take a look at it. Now this table is just for Detroit. And when Doug Balcom originally When Doug Balcom originally did all these calculations, he did it for a number of different cities, and the software that you can get, that's talked about in the course, includes all those different cities and more in it now. But this, once again, is to walk you through it so it doesn't seem like magic, so you can understand it. So if you look at the top of that chart is the load to collector ratio. That's where you look for your number. Okay, so you see how it starts at 200, then drops to 100, then 67, then 50, then 40, then 33, etc. Now think about it. How would you get a smaller load to collector ratio? Well, remember, on the top of that fraction is the heat loss of the house. So if you reduced your heat loss in your house by adding more insulation, then you would have a smaller number. Or if you increased your solar area, that would increase the number on the bottom of the fraction, and that would also make that number smaller. Down below, the load to collector ratio is a description of the different types of solar collectors that we could have. Direct gain is just south-facing window. DG with nighttime insulation is direct gain with just windows with thermal drapes on it. And let me clarify that the characteristics of a good thermal drape is that it has a high R value. It should have some kind of vapor barrier, like plastic, so that you can't get moist air through it to collect on a cold, what will now be a cold window because there's a good drape on it. You don't want water condensing out and coming down the windows and rotting out your sills. So a high R value, a vapor barrier, and it should seal on 3 sides. Now you can do that by hanging your drapes so it touches the floor or it touches the sill. And when the drapes are closed, get some, what's it called? Velcro. And Velcro the sides of the curtains to the wall. Nobody will see that that's there, but it creates an air infiltration barrier. You don't want your air coming behind the curtain, losing its heat, and then dropping and having this reverse thermal siphoning effect where you lose all of this heat out your drapes. So, if you're going to use good drapes, it'll make a big difference. The assumption on this chart is that the thermal drapes that are being used bring the total R value up to an R9. So, as we said, one type of solar system is the direct gain, just a window. The second type is direct gain with nighttime insulation. The third is a trombe wall. That's a mass wall that's behind the window, and it absorbs the sun's rays. The first one has vents, with vents. That's a W slash means with. The second one has no vents. Below that is a water wall. That's windows that has water storage underneath. And then below that is a water wall that has some type of selective black surface, dark surface, so that it's absorbing the sun's rays on the containers of water. Water wall just means containers of water behind the glass. And then you can have water wall with nighttime insulation. In other words, a water wall with thermal drapes. The last three items on there, sorry that it's not coming out, just some kind of reflection, is the sun space, and it's three types of sun spaces. So the first type, which is sun space 60 degrees, is a greenhouse sticking out from the south face of the house that has a 60-degree sun angle. In other words, the glass is angled at 60 degrees, which can cause summertime overheating. It can cause leaks because it's sloped glass. So I'd be careful of that unless you're trying to do some kind of food production too. The second type, I'm going to have you look at it on your sheet because it's not turning out well on the video, is the sun space with 90-degree glass, which can make a lot of sense because in cold areas where it snows, because you get reflection off the snow in addition to the direct gain from the sun. So you actually end up without the problems of overheating from tilted glass or sometimes leakage that you can get from tilted glass, but you still get the same solar gain if you take into account the reflection off the snow. And then last we have a semi-enclosed sun space, and that is where the sun space is more flush with the south face of the house. And that seems to make a lot of sense because if you don't do that, if you have the sun space sticking out from the south face of the house, you will get shading on your other south-facing windows due to the greenhouse. Okay, so now that we've explained that, let me take another look at that chart with you, because the chart is going to help you read off what the solar savings fraction is. We've already calculated our load to collector ratio here as being 177.5. So now we look at the chart, and we also know that the type of system that's being used in this case happens to be a system that has 55 square feet of south-facing glass. Let's take a look at what the chart says. And it's a direct gain system. If you look where it says load to collector ratio, and you see the top line, it says about 200, just underneath that is a solar savings fraction for direct gain of 3. And that's what the sheet says. It says up above, and we interpolate it a little bit. In other words, we adjust it for it being 177 instead of 200. But the solar savings fraction is 3.5. That's a percentage. That means that 3.5% of the home heating needs are going to be delivered by the solar energy. Well, no wonder, given that it's not a very energy efficient house and there isn't very much south-facing glass, that it has such a poor performance. Not a very good design. But at least this system allows you, at least this calculation allows you to see this. The next section is if you have more than one type of solar energy system that you're using, direct gain, plus a sun space, or some other combination. So that's what that section's for. Now let's scroll down and let's see what we can do with these numbers. The next thing we can do is let's find out how much it's going to cost to heat that house. That's step number 5, the auxiliary heat needed. You take the degree days in Detroit at 6,500, you multiply by the net heat loss coefficient that we calculated, 9763. Then you multiply times 1 minus SSF. 1 minus SSF. SSF stands for the solar savings fraction, but we have to change it to a number, not a percentage. 3.5%. Well, I have to tell you more in part 3.